We're going to continue our discussion of stoichiometry problems today by adding in two more conversion factors that we've used before. In the last video, we talked about using molar mass as a conversion factor. Well, this time we're going to add in two familiar ones. We've got the molar volume at STP, which is 22.4 liters of a substance per 1 mole of a substance. And we've got our Avogadro's number conversion factor, the fact that if you've got 1 mole of any substance, you've got 6.02 times 10 to the 23rd particles of that substance. And remember, particles can stand for atoms, molecules, or formula units. So that term can stand for any of those units. So let's start out with this first problem, attack it the same way. How many liters of oxygen, we're looking for liters of oxygen, are needed to produce 20 grams of SO3 at STP? Just seeing that STP should clue you in that you are going to possibly need to use that 22.4 liters per mole. So let's label everything like we've been doing. We need X liters of oxygen, and we're trying to produce 20.0 grams of SO3. So we're Xing out SO2. We're underlining our coefficients so we can make our mole ratio. And our mole ratio in this case is going to be 1 mole of oxygen for every 2 moles of SO3. X out those coefficients if you wish, so you don't try to use them again. And let's start the problem, as we always do, with what we've got underlined. We've got 20.0 grams of SO3 over 1. And since we started with grams, our only conversion factor that involves grams is our molar mass. We add up 1 sulfur and 3 oxygens, and we get 80.07 grams of SO3 per mole of SO3. Grams of SO3 cancel. We're at moles, and remember in stoichiometry, our goal is to get to moles as soon as possible so that we can use our mole ratio. Looks like we need moles of SO3 on the bottom. So as is for our conversion factor, our 2 moles of SO3 per 1 mole of O2. That's going to cancel moles of SO3. Do we want moles of oxygen? No, we want liters. Do we have a conversion factor that involves liters and moles? Why, yes, we do. It's our molar volume at STP. We need moles on bottom, so our 1 mole of O2 is going to go on bottom. Our 22.4 liters of O2 is going to go on top. So that's going to cancel moles of O2 and leave us with liters of O2. So when I take 20 divided by 80.07 times 1 divided by 2 times 22.4, I get 2.79755. And remember that value, that interim value, before we get it in correct Sig Figs and scientific notation, does not have to be there. Since it already has our decimal in the correct place, all we really need to worry about is our Sig Fig. So looks like we've got 3 Sig Figs for our 20.0, 4 Sig Figs for this molar mass, and 3 Sig Figs for our molar volume. So it looks like we're going to need 3 Sig Figs for our answer. Draw our Sig Fig line. You can put times 10 to the 0 if you want to. I choose not to. So looks like we're going to need to round up to 2.80 for our numerical value, and liters of O2. Let me get that in. Final answer, color. Liters of O2 for our liters of oxygen. Now, it could say volume here. If it says volume, it's looking for liters. So watch for that. That might prop up on a couple of problems. Okay, our final example. How many molecules of SO3, as soon as it talks about molecules, that should be giving you a clue of what kind of conversion factor we may need to use, would be produced at STP from 5 liters of oxygen, and yet another conversion factor we might use. So we've got the same balanced equation, the fact that 2 SO2s plus O2 is going to yield 2 SO3s. Got to have that balanced equation. So labeling it, we've got molecules of SO3. Be careful, SO2 versus SO3, you'll make a mistake and mark the wrong one, so make sure you're marking the correct one. So X molecules of SO3 is what we're looking for, and we're given 5.00 liters of oxygen. X out SO2, make your conversion factor that there's 1 mole of oxygen for every 2 moles of SO3. And now we're ready to start the problem with what was underlined in the question, 5.00 liters of oxygen. Make sure you're putting the same formula for oxygen in your problem that was there in the balanced chemical equation, because if you just put O, it could end up giving you the incorrect answer if you're dealing with molar mass. So 5 liters of oxygen. The only conversion factor we've got that deals with liters is our molar volume. We need liters of oxygen on bottom, so that means our 1 mole of oxygen must go on top. 22.4 liters of oxygen. That's going to cancel our liters, leave us with moles. As soon as we get moles, we know we need to use our conversion factor, our mole ratio. So moles of O2 on the bottom. Now look at the conversion factor. It looks like we're going to need to flip it this time with the 1 mole of oxygen on bottom and the 2 moles of SO3 on top. So pay attention to where the units go for those mole ratios. That's going to cancel or reduce to 1 our oxygen. Now we've got 2 moles of SO3. Guys, after doing the mass-mass stoichiometry, it's very easy to just slap up a molar mass here. But that's not what this problem is asking for. It's asking for molecules. So make sure you're using the correct conversion factor. I need moles of SO3 on bottom, and all of those conversion factors, remember, are based on 1 mole. But I need Avogadro's number, 6.02 times 10 to the 23rd, molecules of SO3 on top, not a molar mass. So moles of SO3 cancel. I'm left with molecules. Do yourself a favor and always double check that your final circled answer matches what's circled in the problem. So when I take 5 divided by 22.4 times 2 times 6.02 times 10 to the 23rd, I end up with 2.6875 times 10 to the 23rd. It's already in scientific notation. Make sure you plug those values correctly into your calculator. As far as Sig Figs are concerned, we've got 3 Sig Figs here, 3 Sig Figs here, and 3 Sig Figs here. That's pretty obviously 3 Sig Figs. So looks like that very next number, 7, makes us need to round up. So my final answer becomes 2.69 times 10 to the 23rd molecules of SO3.